Today we're talking probability and statistics from the FE engineering exam, and we're looking at the laws of probability. These are things that a lot of people have trouble with just from a logic standpoint. They don't end up being super complicated, but we'll go through the three laws, and you see the first two there from your handbook, and then we'll look at a problem that is a good example, I think, of applying some of these laws. So when we talk about probability, again, cut out directly from the handbook, first law of probability, the probability of an event is going to range from 0 to 1, right? So intuitively, this makes sense. If something isn't going to happen, it has a probability of 0. If it's definitely going to happen, it has a probability of 1 or 100% probability. And then most other events fall in the middle somewhere. So one consequence of this is that if we have an event A, we can define the probability of A happening, and it'll be somewhere between 0 and 1, right? Just as the rule says, just as we talked about. But we could also have another event, and we can call it not A. And again, this same thing. We'll have the probability of not A. It'll fall between 0 and 1. So you can think of it, if this is just a binary event, the probability of A is the probability that an event will happen. The probability of not A is the probability that the event will not happen. And when you have a nice binary event in this type of instance, we could say that the probability of not A is 1 minus the probability of A, right? If 1 is 100%, the probability of something happening is 100% probability minus the probability of that thing happening. So if you're 30% likely to go to the store today, then you are 100 minus 30, you're 70% likely to not go to the store today. And we'll see how to use this. If we go on to our second rule of probability, this is the law of total probability. And we could see here we're dealing with an or situation, right? It defines it right here for us in the handbook, the probability that either A or B occur alone or that they occur together. So a lot of times people will draw circles to really define this well. So we're going to draw a circle here and say that this is event A, and then we'll draw a circle here and say that this is event B, and then this space in the middle, we can call this probability of A and B, right? This is going to be end. And there doesn't have to be overlap, right? These two circles could be discrete. Maybe there is no probability that both things happen, but there could be, so we have to consider that case. So now if we look at this, the probability of A or B happening is the probability of A happening plus the probability of B happening, and we'll do vertical lines here. And that's this part. And now you have this interesting piece here, minus the probability of A and B. Well, why are we minusing that? Well, when we counted A, we included the things that belong to A but not A and B. And when we counted B, we included the things that belonged to B and not A and B. And in both of those instances, we counted the things that belong to A and B. So you could see there's an overlap between my diagonal lines and my vertical lines. So this was counted twice when we did probability of A plus probability of B. So we have a duplicate there. So we have to get rid of that duplicate, that overlap. So that's why we're subtracting out the probability of A and B. So now if we do this, we will get the situation where event A can occur, event B can occur, or both events can occur. And now let's look at the third law, law of compound or joint probability. So in the second law, we looked at the either or both case. Here we're going to look at the and case. So probability of A and probability of B. We can see we've added this vertical line here, and this really represents some dependence. So the probability that two events that end, they have both occurred, is the probability of the first event multiplied, we're not doing addition now, multiplied by the probability of the second event, probability of B, given that A has occurred. So again, you could have discrete events here, and B could not be dependent on A, in which case this would simplify to just the probability of A times the probability of B. So let's look at a quick example to illustrate the difference between properties 2 and 3. So we'll start with property 3. And let's say we have a fair dice, and we're going to do 2 throws of the fair dice, right? A dice isn't like a deck of cards where if you remove a card, it changes the probability of picking a certain card in the next draw. With a dice, you're going to have 6 faces on the dice when you roll it the first time. You're going to have 6 when you roll it the second time. So let's talk about 2 events. So PA, probability of A, will be that the first throw is even on a dice, so it gives us a 2, 4, or 6. And the probability of B, the second event, is that the second throw is a 4. Okay, so now we have probability of A, probability of B. So let's say we want to find probability of A and B. So we want to find the probability that the first throw of the dice is even and the second one is a 4. Now remember, we said that there's some dependency here, but the second throw, you getting a 4 on a dice roll, is not dependent on the first throw. So we simplify to this nice, easier case of just simple multiplication. So the probability that we throw an even is 3 out of 6, right? 2, 4, and 6 are even on the dice, or 1/2, we can say. And the probability that we get a 4 on our second throw is going to be 1 out of 6. So probability of both, we'll draw a little line here. Probability of throwing even and then a 4 is going to be a half multiplied by a sixth. So it's going to be 1/12. So now let's contrast this to the probability of A and B. And we'll hop back to refresh your memory. We want the probability of A, B, and the combined probability. So now we've done some of the work for ourselves, right? Because we have the combined probability there. So now we can do the probability of A, which is a half, plus the probability of B, which is a sixth, minus the probability of both, which is 1/12. So now we can work this out, right? So 1/2 is 3/6, or actually, I guess we should do this in twelfths to make it easier on ourselves. So 6 out of 12, and 1/6 is 2 out of 12, minus 1 out of 12. So we're going to end up with 7/12. Right, so there we can compare and contrast. So let's take a look at a problem that's kind of typical of what you might see on the FE exam. So we have a basketball player whose probability of hitting a shot, hitting a free throw, we'll say P of F, we'll call that, it's 4 out of 7. And remember from our first rule of probability, the probability of not hitting a free throw then is 1 minus 4 out of 7, so it is 3 out of 7. All right, so now we have the probability of hitting a free throw, probability of not hitting a free throw. And we want to know what is the probability that he hits a free throw in at least 1 out of the next 4 shots. So this at least, this is your kind of key thing to fixate on here. When you see at least, there's a very interesting approach that you can take to a particular problem. So this player is going to shoot 4 shots, and you want to make sure that at least one of those is a successful free throw. So there's a few ways you can do this. You can find the probability of him hitting all 4 shots, then 3 shots, then 2 shots, then 1 shot. That gets very complicated. Or you can think of this another way. So the probability of him hitting at least 1 is 1 minus the probability of him hitting none. Right? We're following our first rule there. You want him to hit at least 1, so you're taking the probability of him hitting none out of that full amount of 1 or 100%. So what is the probability of him hitting none? Well, it's the probability of him not hitting 1 on the first shot times the probability of him not hitting 1 on the second shot times the probability of him, not hitting 1 on the third shot times the probability of him not hitting 1 on the fourth shot. Right? This is using our third law. So this is using our first rule. This is using our third one. Because now we're using an AND case. he doesn't hit the shot on the first one, and he doesn't hit it on the second one, and he doesn't hit it on the third one, and he doesn't hit it on the fourth one. And as we said is the case with the dice, when you're shooting a basketball, there's no dependence, right? You could make the first shot and miss the second, or vice versa. You can make them both, but your first basket doesn't affect any future performance, at least if you don't consider psychologically. So we're going to find 1 minus that probability. So what does this look like? Well, we already said up here that the probability of not hitting a free throw is 3 out of 7. So we're going to do 1 minus 3 out of 7 4 times. And if we really wanted to, we could, of course, write this as that. So when we work out the math here, what do we get? Well, we get, if you plug it into your calculator, about 0.96626, and so on and so forth. So you can see we're pretty close to 1. There is a 96.63% chance that if you're a free throw shooter who hits 4 out of every 7, if you have 4 tries, you're going to hit at least one of those shots. Now remember, by doing this 4 times, we're considering this probability includes the situation where you hit 1 out of 4 shots, 2 out of 4, 3 out of 4, or all 4 out of 4 shots. We're just removing the one case right here where you miss every shot.